At the end of last week's lecture, a student asked me, can we always use repeated substitution to find a closed form? Or, more generally, does every recursively defined function have a closed form? Now, a little embarrassingly, I couldn't come up with an example on the spot, so I said I would make a video instead. And here it is. Consider the following recursively defined function on the natural numbers. F of n is 1 if n is equal to 0 or 1, and f of n is equal to n times f of n minus 1 if n is greater than 1. Now you can certainly use repeated substitution to try to find a pattern if you like, or you might notice that this is exactly the definition of the factorial function. And now you might be thinking, David, this is a bad example. Here's your closed form right here. But the reason I'm bringing this up is so that I can talk about a little subtlety when it comes to defining what a closed form actually is. So if we actually wrote out what n factorial was, we'd get the equation f of n equals n times n minus 1 times ... 2 times 1. And if you imagine, say, writing a computer program to compute this, well, we'd expect that this sequence of operations would take linear time. But one of the key features of the other closed forms we've seen so far, for example, n squared, or n log n, or n over 2, is that these can all be computed in constant time. The number of calculations we need to do doesn't depend on what n is. And that's not true here for the factorial function. And so n factorial is not a closed form. Another common expression which is not a closed form is the sum from I, say, equals 0 to n of I. For the exact same reason. It takes linear time to compute. But we know by now that the sum of the first n natural numbers does indeed have a closed form. What about factorial? It turns out we don't know what the closed form of n factorial is. Something we'll do this week is return to the notion of asymptotic bounds. So even if we don't have exact values, we can still say something about the rates of growth of certain functions. For the factorial function, it's actually pretty well known that it's less than n over 2 to the n for all n, and it's greater than n over 3 to the n. By the way, in case you haven't seen this before, this implies that the factorial function is huge. It grows faster than any exponential function even. But actually, using some basic calculus, you can show that the upper bound and the lower bound in this case, they aren't tight. There's a large gap between them. So even better than this, we have Stirling's approximation for n factorial, which says that n factorial is asymptotically equal to root 2 pi n, n over e to the n. And in case you're wondering what this symbol over here means, that means that the limit as n goes to infinity of n factorial over root 2 pi n times n over e to the n, that limit is equal to 1. So as n goes to infinity, they have the exact same order of growth. And just in case you're interested, the last thing I'll say is that in 2011, Mordechai proved an even tighter asymptotic relationship, which is that n factorial is asymptotically equivalent to 2 pi n square rooted times n over e plus 1 over 12 en to the power of n. And this is the best known approximation to date. So I hope you liked that little math tidbit. Thanks for watching and have a great day.